We're now going to continue on with our discussion of the various examples for the Java fork join pool. If you recall, we talked about the applyAllItter implementation, which just looped through all the various fork join tasks and started them off, all running initially in a single thread that was then stolen. Its deck was stolen from by other threads in the fork join pool in order to be able to disperse the processing across multiple elements, multiple threads in the fork join pool. And then we talked about something called applyAllSplit, and that was a very clever approach that used a splitter task and a list, actually a series of lists, in order to break the overall problem up into smaller chunks. And now we're going to come back and take a look at yet another way to do this by a new implementation called applyAllSplitIndex. And this approach also uses recursive decomposition to disperse tasks to worker threads. But as we'll see, it does it in a somewhat more lightweight way that doesn't require making copies of lists all over the place. So once again, we're going to have the driver method, which is called applyAllSplitIndex in this case. And what it's going to do is it's going to apply an op, which is a function, to all the elements in a list, which is a list of t, using the fork join pool that's passed in. And you can find this in my fork join utils.java file in the ex22 folder. So the first thing we're going to do here is we're going to create a new array to hold the results, because we're not going to be doing things that involve sublists this time. Instead, we're going to create an array, and then we're going to store the results directly into the array. Now, this is also a very interesting example of how to create a generic array in modern Java. And what it does is it has to use reflection for a whole bunch of really wacky and weird reasons having to do with type erasure and the Java generic semantics. And yes, it's very ugly, but that's the way you do it. If you want to make a generic array, you have to do something along these lines. So once we've got this array, then we're going to make ourselves a splitter task, except unlike the implementation that we used earlier, which used recursive task, this one is going to use recursive action. It's still going to partition the list recursively and run each of the halves in a fork join task, but this time it's going to use a recursive action instead of using a recursive task. And we'll start off here by using the invoke method on fork join pool. If you recall, that's a blocking two-way call that will start with an initial task, and then, as we'll see, that task will recursively decompose itself. And the invoke method will wait for all the processing to be done before it actually returns back to the caller. As you can see here, we're passing in 0 as the first parameter to the initial splitter task, and then list.size. So we're going to be passing in indices as opposed to making copies of sublists. And of course, we're going to start with the entire elements of all the lists to begin with. When we're done, we're going to take the results array that we compute everything into with our splitter task implementation, and then we're going to convert that back into a list. And in this particular case, we're going to use the arrays.asList method. There are other ways we could do that, but this is a clever way to do it. Note that there is some overhead here of going from a list to an array back to a list, but you'll see that we don't have to do any copying of sublists. And we'll also take a look at yet another even more clever way to optimize this when we get to the end. So the alternative way of doing this, which you can see requires a slight change to the applyAllSplitIndex signature, is to pass in an array as a fourth parameter. And so this way of doing things is more elegant because we don't have to do this crazy reflection-based approach to make a new array. And it's also more efficient because we're not going to have to convert things back and forth between a list to an array back to a list again. So as we'll see when we run the test, this is a little bit faster, but we'll come back to that in a bit. So here's the splitter task that we're going to implement this time. Notice this one's going to use recursive action, not recursive task. And as you can see, this implementation is very similar to the one we did before, except it's going to work on this array as opposed to working on sublists. So let's take a look and see how this works. We're going to keep track of the array indices, the low and the high, and those, of course, will be used to index into the results array that's passed in either as a parameter or we create using reflection at the top of this whole method. Here's what the compute method looks like for our new implementation of splitter task. That's the piece of code that's going to recursively perform all these computations in parallel using the fork join pool. The first thing it's going to do is it's going to figure out the midpoint in the current range. So we take the low plus the high, and then we right shift by 1, which is the same thing as dividing by 2. Just a bit more obscure, but they basically work the same. And that'll compute the midpoint. And if low equals mid, then that means we're basically have a single element to work with, in which case what we do is we go ahead and get that element from the list using the get method and the mlow index. We apply the function op in order to compute the value, and then we go ahead and store that in results sub mlow. So that's how we do it. That's the base case for the recursion. If we don't have the base case, if we have something that's got 2 or more elements in it, then we're going to go ahead and create a new splitter task. And notice how we pass in mlow, and then we pass in mid, and we update mlow. And we'll make the new task to handle the left-hand side of the list. And then we're going to go ahead and fork it. So we make a new splitter task for the left-hand side of the list. We fork it, and then we store that in fork join task void, because there's no return value, called LT for left side task. So that's got ourselves the left side that's been forked, that's been arranged to run in the fork join pool. And you'll notice that the way this works is the way we've done it before with the other applyAllSplit method, where we're going to have larger partitions pushed onto the deck before the smaller ones. And that, of course, helps with work stealing. Then we call the compute method, and that will compute the right-hand side in parallel with the left-hand side. So notice over here, we updated mlow to be mid. So now when we call compute, it's going to work on mid to the end. That's what we're going to do there recursively, while the left-hand side is going to be running in parallel by forking. And notice that we have the compute method run in the same task as its parent in order to minimize context switching. So we only have one thing at a time that's put onto the deck in order to run in parallel. Then after we're finished computing the right-hand side, we then go ahead and wait for the left-hand side to finish. It could be done already, in which case join returns immediately, or it may wait a little bit in order for the left-hand task to finish. In either case, when join returns, then we are complete at running the computations on this particular segment of the array. And at that point, all the contents will be in that results array. And notice that join is a synchronization point. And what that means is that all the state from the different threads will be pushed out to the different threads and then running on the different cores. And you can read more about that in the link at the bottom of the slide below. There's no need to merge anything in this approach because everything's already been stored back into the results array by virtue of the way that the base case of the recursion behaved. Now, this implementation is arguably a little bit harder to understand and arguably a little harder to program than our approach earlier that was the applyAllItter implementation that just walked through the original list and just did basically fork, fork, fork on each of the items. So there darn well better be a benefit that comes from doing things this way. Otherwise, why go to all this trouble? Before we look at the performance of this versus other approaches, though, let's first spend a little time visualizing the applyAllSplitIndex method. And as before, it works very similarly to the other applyAllSplit implementation, just doesn't end up having sublists, but instead uses these indices. That's what are passed through the splitter task. So as you can see, what we do here is in the non-fork join task client thread, we're going to go ahead and call invoke and pass in the enclosing splitter task, the one that has all the elements in it. And that will be put onto the shared queue in our fork join pool that we're using to call invoke. At this point, then things start to get interesting. So when compute starts to run, notice what we're doing is we're forking, and then that will be put onto the queue. And then when that runs, that will further fork, and that will be typically taken by a different thread. And so what we have here is we end up basically recursively decomposing all these subtasks onto the worker threads in the pool. And the nice thing about this is that work stealing is low because we're doing this recursive partitioning. Copying overhead is low because we're not doing sublists that require all these copies. Although we are making a bunch of recursive method calls, which isn't the end of the world because that's pretty heavily optimized in modern Java runtime environments, but it's higher than what we were doing before with the applyAllItter method, which didn't have to do any recursive calls at all. As you can see here, the forked subtask and the compute call can run in parallel because these are both going to be running in different threads. And the join doesn't return any values, of course, because everything's been stored into the results array. And its only purpose is to serve as a synchronization point to make sure that all the state gets pushed out to the various processor core caches. And the nice part about this is also there's a relatively balanced tree of join calls. So once again, it's more efficient and everything can be pitching in properly and running. So we'd expect, hopefully, the performance would be a little higher than the other implementation that we looked at earlier for applyAllItter. So that's the end of the overview of the applyAllSplitIndex version of this fork join framework programming model. And now what we're going to do, now that we've finished looking at all the different implementations, we're going to actually compare and contrast them in terms of their actual performance results.